Well, our 2-hour delay turned into a cancellation, so here I am still making lesson videos. So last class we talked about evaluating limits by using a table and looking at what the y values are approaching, or looking at a graph and analyzing that way. Today's lesson is how we find the exact value of a limit analytically. Analytically often means algebraically. Through algebraic methods that you guys have learned, how can we do it? So it says, remember, the limit of a function as x approaches c does not depend upon the actual value of f of c, but what happens as you approach c from the right and the left. So we care about what's happening as we approach that target x value, not what's happening at that x value. However, if you have a continuous function at some point, so this whole thing about what was happening as you approach was to combat that issue of a non-continuous function. Like if you had a hole, you could still approach that hole. However, if you have a continuous function, it actually turns out rather nicely. What you're allowed to first try to evaluate a limit. So like if I look at this right here, the limit of 2x plus 5 as x approaches 3. Now you could graph this line and then see what is happening as x approaches 3 from the left and from the right. But this is a continuous function at 3. This is a line, which means our limit is actually going to be the same thing as what the function is at 3, since this is continuous. So we're allowed to try direct substitution to analyze any limit to begin with. What that means is, to analyze this limit, I can plug 3 in for x and see if I get a value. And if you do, that value is your answer. So if I plug 3 in for x, I get 2 times 3 plus 5, which is 11. So if we would graph this line, then as x approaches 3 from the left and the right, our y value is going to be approaching 11. So pretty nice and easy. I will also say this. This is the first thing you should try to do anytime you're analyzing a limit. However, what you're going to find, this is almost never going to work with the questions that you're given, and for the calculus techniques that we're trying to get towards, it's rare that you'll be allowed to just plug this number in and then get your answer. Okay, so we'll talk about other options if that doesn't work. Well, as with any topic in math, there's always properties. So like you learned exponents and then you learned properties of exponents. You learned logarithms, you learned properties of logarithms. So there's also properties of limits, things that you're allowed to do to kind of make your life a little easier. So it says let b and c be real numbers and let n be a positive integer. Okay, so let's look at some things that turn out to be true. If you take the limit of some constant, so b is a number, some constant, as x approaches c, your answer is just going to be whatever that constant is. And try to think about why. So we'll do this first example and then we'll think about why. So this says find the limit of 5 as x approaches 4. Now this right here could be anything. This could be as x approaches 1 trillion, and this answer is still going to be 5. Now again, let's try to understand why. Because if we would graph this line, y equals 5, because remember, a constant is just a horizontal line. So I'm going to graph that line, y equals 5. No matter what x is approaching, if I find the limit as x approaches 1, well, our y value is approaching 5 from the left and the right. If x approaches 2, 5 again. So it doesn't matter what x is approaching. If you have a horizontal line, your limit is going to be whatever that value is. Next one just comes straight from the direct substitution. These aren't really properties that you kind of have to memorize. If you understand limits, you don't have to really use these properties. But if you take the limit of x as x approaches c, well, x is a continuous function. It's a line. So you could plug c in for x, and that gets you your answer. So if you take the limit of x as x approaches 4, well, plug 4 in, use direct substitution, you get your answer. When you use direct substitution, the limit part goes away. That's something that I want you guys to see here. When you use direct substitution, then the limit, you're now applying the limit, and the limit is gone. This next one is still just direct substitution, plugging c in for x. So right here, the limit of x cubed as x approaches 2. Direct substitution, plug 2 in, 2 cubed is 8. So direct substitution works. Why don't you go ahead and maybe pause it and try examples 2 and 3 here. Okay, so I'm going to try direct substitution. So I plug 2 in, and let's see if I get a value. Now be careful with your negatives and things like that. So the way I'd write this is negative parentheses 2 squared plus 1. So now this is negative 4 plus 1 gives me negative 3. And also, anytime you get an answer in this class, I want you to think about what your answer means. You're going to be doing a lot of algebra skills in this class, and you're going to be able to use the skills just fine and get a lot of answers on your own and get the right answers. But I want you to think about what you're finding. What we just found is if we would graph this parabola and approach 2 from the left and the right, the y value is going to approach negative 3. That's what we're finding. And I can do the same thing here. Let's plug 1 in for these x's and see if it works. So 3 times 1 cubed minus 2 times 1 squared plus 4. So PEMDAS says do exponents first. 1 times 3 is 3, minus 2 plus 4, so we get 5 for our answer. So here's a little theorem. It says if p is a polynomial function and c is a real number, then the limit of p of x as x approaches c equals p of c. Really, they're just saying you can use direct substitution. Because a polynomial function, the reason why we study polynomials so much in algebra and in pre-cal and things like that, anytime you're given a polynomial function, remember what that means. That's like, it could be a constant, it could be x squared, it could be 4x cubed, it could be 8x to the 5th plus 3x squared plus 1. These are all polynomials. And polynomials are really nice to work with because they're always very smooth and continuous. There's no like jagged points, there's no discontinuities. There's always nice smooth curves depending on what the degree is. And so they're always continuous and nice and smooth. And so anytime you have a polynomial function, direct substitution is going to work. That's what this says. Now if you have a rational function, so a fraction, and c is a real number, such that the denominator does not become 0 when you plug it in, then the limit of that rational function, you can use direct substitution. Again, so long as your denominator is not 0, because you can't divide by 0. So if you try direct substitution and you get 0 in the denominator, then direct substitution doesn't work. And that's going to lead into something we're going to talk about here in just a minute. So we have a rational function here. And we always hope direct substitution works. And it will, because if I plug 2 in, I'm not going to get 0 in the denominator. So I'm going to be allowed to use direct substitution. So let's plug 2 in for both x's. And we're going to get 6 plus 5 in the numerator, negative 5 in the denominator, negative 11/5 for our limit. Some more properties of limits. And these ones are a little more useful than the other basic ones we talked about. Okay, so we're given the limit of a function as x approaches c. In fact, the limit of f as x approaches c is 3/2. And the limit of g, some other function, as x approaches c is 1/2. And here's how we can apply these properties here. If you have, and this is going to be a big concept throughout this course, if you have a constant multiple, meaning a number being multiplied to some function within your work, within a limit, you can actually pull that number out in front of your limit and write this as 4 times the limit as x approaches c of f of x. Now be careful using this because sometimes students want to pull numbers out of trig functions. Like if you were given sine of 4x or something like that, you can't pull a number out in front of a trig function. So be careful when understanding this property. If you have a number times some function in your limit, you could pull that number out in front. What that lets you do now, we know what this is. They gave us this here. The limit of f as x approaches c equals 3/2. And that's what this is saying. So this is 4 times 3/2, which is 6. If you have the limit of a sum or difference, so if you have like functions being added or functions being subtracted, you can actually split this up into limits of each one being added or subtracted. So you could write this as the limit as x approaches c of f of x plus the limit as x approaches c of g of x. So again, we say the limit of a sum equals the sum of the limits. And same goes for difference. I could just easily put plus or minus inside of here. But since this one says plus, what that lets us do is we know this one is 3/2. We know limit of g as x approaches c is 1/2. And 3/2 plus 1/2 is 4/2, or 2. Well, just like limit of a sum is the sum of the limits, the limit of a product is equal to the product of the limits. So we could write the limit as x approaches c of f times the limit as x approaches c of g. So the limit of a product is equal to the product of the limits. And we know, again, what each one of these is. This is 3/2, this is 1/2. 3/2 times 1/2 is 3/4. Multiply as share your costs. And just like the other two, the limit of a quotient is equal to the quotient of the limits. So this would be the limit of f as x approaches c divided by the limit of g as x approaches c, which means we can just substitute right off the bat. Let's do 3/2 divided by 1/2. Remember, when you divide fractions, that's like multiplying by reciprocals. So 3/2 times 2/1. 2's cancel, you get 3. So just some properties that you're going to come across as you do your analytic methods. The next one is rare to show up, but it deals with the composite function. So you have two functions here, and it says the limit of g of f of x as x approaches -3. Now, this property says this outer function, this g function right here, we can actually, I don't want to say pull it out, but we can write it in this way. We can write this as g of the limit as x approaches -3 of f of x. So you could take that outer function and just have it be g of this limit here. And so now we can find this limit. They tell us f is x plus 7. So the limit of f as x approaches -3, well, let's direct substitute. Let's put -3 into the f function, and we get 4. This limit is 4. And so now we're looking for g of 4. Well, g of 4 is 4 squared, so 16. So the limit of a composite function, you're allowed to take that outer function and write it in this form. So we have the limit of f of g of x as x approaches 6. Well, we can write this as f of the limit as x approaches 6 of g of x. And we can find the limit of g as x approaches 6. Put 6 in for the g function, you get 36. Now we have to find f of 36. So 36 plus 7 is 43. All right, last page. So I mentioned how direct substitution is not always going to work, unfortunately. It's actually rare if you get a question where it actually does work. Now your homework tonight, it might work because that's what we're assessing for the most part. But let's say this happens. I want the limit of this function as x approaches 2. Well, if I plug 2 in for these x's, all right, I'm just going to try direct substitution right off the bat. So I plug 2 in and I get 4 minus 14, so -10 plus 10, I get 0. And then 2 minus 2 is 0. 0 divided by 0 is inconclusive. There's nothing, it's not 1, it's not 0. 0 divided by 0 is undefined. In fact, this is called an indeterminate form. This is called an indeterminate form. There's nothing that you can determine when this happens. The other indeterminate form that we'll come across is if we plug a number in and we get infinity divided by infinity. That's the other one. So there's infinity over infinity and 0 divided by 0 are two issues that arise. You can't conclude anything. This is not one right here. In fact, there are varying degrees of infinity. Things get to infinity quicker than others, things like that. We'll get into all that stuff. But we can still analyze this. So we don't just say the limit doesn't exist. All right. Here's what we do. We look for an analytic way. Is there a way we can simplify this? And in fact, there is. We can factor this numerator. We can factor into x minus 2, x minus 5. And then the x minus 2's go away. The reason direct substitution didn't work right off the bat is because there's a hole at x equals 2. If you would graph this, there's a hole at x equals 2. So what we're doing is eliminating that hole. Because remember, we don't care what's happening at x equals 2. We care about what's happening as x approaches 2. So by factoring and canceling, we now have the limit as x approaches 2 of x minus 5. And now we can try direct substitution again. So we've eliminated the hole. Now we plug 2 in for x, and we get 2 minus 5, which is negative 3. And really what this is telling you is, in this original function right here, there was a hole at 2, and in fact, that hole existed at 2 comma negative 3. That's what this is finding right here. So that's one analytic way. If you try direct substitution and you get 0 over 0, see if something factors and cancels, and then try direct substitution again. Okay, so that's option 1, factor. The next thing, so I'm going to try direct substitution. So I plug negative 1 in, and I'm going to get 1 plus 8 is 9. Square root of 9 is 3. 3 minus 3 is 0. So I get 0 on top, and then 0 on bottom. So I get 0 divided by 0, indeterminate. But I don't just say the limit doesn't exist. What I now want to do is see if there's another analytic way to deal with this. Now there's nothing to factor, so I can't use what we did here. In Algebra 2, and maybe in Pre-Cal, and maybe in Algebra 1, I don't know how often you do this, you talk about a method about rationalizing the denominator. And so that is when you try to get rid of the radical in the denominator. And there's not really a reason why you do that in Algebra 2. The reason used to be because you had to, in order to use the abacus, you had to divide by rational numbers. Well, we don't have abacuses anymore, so it's kind of an outdated notion. The skill, however, is actually more beneficial to rationalize the numerator when we're dealing with calculus. So I want to try to get rid of this radical from the denominator. And you'll see what happens and why we're trying to do this. So I want you to think about how to rationalize something. And again, in Algebra 2, I taught you guys this. So like if we had this, and I wanted to rationalize the denominator, well, we had to multiply the top and bottom by the conjugate of this. So the thing we would multiply by would be 3 plus radical 5. Hopefully this rings a bell. And in doing so, this is going to eliminate the radical from the denominator. So I'll keep going here just to refresh your memory. So you would get 6 plus 2 radical 5. And on bottom, we would distribute this out. So you would get 9, and then plus 3 radical 5, minus 3 radical 5. So those are going to cancel, and then minus 5. And so you get 4. And you can, to keep going, you could divide these by 2 and simplify that more. But I'm just trying to get into the skill here. So here, I want to actually rationalize the numerator. So I want to multiply the top and bottom of this by the conjugate, which really means we flip this sign between the radical and the non-radical. The plus 8 will stay, but we're going to change this to a plus 3. So here's what this looks like. We're going to multiply by the square root of x squared plus 8 plus 3 over square root of x squared plus 8 plus 3. And to do the multiplication, I like to put everything in parentheses just to show that we are going to be distributing. I do this anytime I'm multiplying quantities together. Okay, so let's see what happens. When we do this, if you're not applying the limit and using direct substitution, you are going to have to write this thing right here through each line of your work. Some people try to find a shortcut and they'll say, I'll just remember to put that back in at the end. And that doesn't fly. Every line you write needs to be equivalent to the line above it. You can't just save it for the end. So when we write our next line, we have to write the limit as x approaches negative 1. Well, now let's see what happens on top. When we multiply these two things together, we just get x squared plus 8. The whole point of doing the conjugate is because the outer and inner terms are going to cancel. It's the reason we do it. So we don't even really need to think through that. And then minus 9. Now on bottom, you could distribute this out, but I don't want you to. And the reason is, you'll see why in a second, but just to give you a heads up, the reason being, the thing that was causing us the issue in the beginning was this x plus 1. The reason we have to try something different is because when we plugged -1 in for x, we got 0 down here. This is our issue. We're trying to get rid of this factor of x plus 1 down here. So leave it factored out. So I'm just going to write this as x plus 1, and then square root of x squared plus 8 plus 3. And the reason being, we're trying to get this to go away. So now let's see what happens. So we have the limit as x approaches -1. The numerator we can clean up. That's going to be x squared minus 1. Well, think about x squared minus 1. That's a difference of squares. X squared minus 1 factors into x plus 1, x minus 1. And on bottom, we still have x plus 1, and then square root of x squared plus 8 plus 3. And I'll wait a second for you guys to write this because I don't want the concept to get lost on you here. Going back to the beginning, we are trying to get rid of this thing here. This is our problem. That's our problem right there. Well, now look at what happens. We can actually get rid of it. Gone. Gone. We've eliminated the problem. Eliminate the problem. So it's gone. So now we can use direct substitution with what is left over. So now let's plug -1 in. Now at this point, when we're using direct substitution, we no longer have to put the limit. We're now applying it. So we're going to have -1 minus 1 on top. And then here we're going to have square root of 9, so 3 plus 3, which is 6. So -1/3. So even though initially we tried direct substitution, it didn't work, well, now we eliminated the issue through rationalizing. And those are usually going to be your two go-tos. We'll talk about another one as well, I think in another lesson. But you're usually, when you try to plug it in, it doesn't work. You're going to factor and cancel, or you're going to try to rationalize and then see if you can then use direct substitution. All right, last couple of tidbits. So we're going to learn quite a few theorems in this class, just like you did in geometry. And it is really important that you guys can read math in this class. So when I read this theorem, yeah, I'm going to kind of give you the more intuitive version of it, but I don't want you to just wait for the intuitive version. I want you to try to make sense of what math says. I think that's going to help you a ton when we actually get into the meat of this class. So here's something called the squeeze theorem. Sometimes it's called the sandwich theorem, but here's what it says. If you have 3 functions, and one is always in between or equal to the other 2 functions. Okay, so you have 3 functions, and one is always in between the other 2 functions for all the x values in an open interval containing c, except possibly at c itself, some x value. And if the limit of this function as x approaches c equals L, and the limit of g as x approaches c also equals L. So if these outer functions have the same limit as x approaches c, and this one is always in between these two or equal to, then the limit of the middle one as x approaches c is also equal to L. Now here's what this says. I want you to see this graphically and what it means, okay? So we have some function g that's always greater than the other two. So we have some function up here, g of x. All right, that's your uppermost function. And then we have some function h that is always below g. It could touch g, and that's h. All right, and the reason I'm going to have them touch is for this theorem because it says they have the same limit at a particular x value. And so where they're touching right here, I'm going to call that x value c. And that limit, as x approaches c, like each one of these, it's approaching L right here. That y value is some limit. It doesn't matter what it is. Call it L. And then what the conclusion says. So here's all the setup. All right. Any theorem we do, there are always conditions that have to be met in order for the theorem to apply. We always focus on the conditions. What has to be true so that the conclusion of the theorem is then satisfied? Well, this is true. We have two functions. One is always above or equal to the other. And the other condition is their limits at the same x value are equal to each other. So we've met the conditions of the squeeze theorem. Now here's what it says. If you have another function in between them, so it's always in between or equal to, well then as we get to this place right here, it can't go above that or below it or it breaks this condition. So it has to kind of squeeze through there, right there, in order for our conditions to be upheld. So this is f, and it's in between g and h, and also or equal to. And what the conclusion says, if g and h have a limit of L as x approaches c, then f has to have a limit of L as x approaches c. It has to, because it has to go through that point right there. So to kind of put some numbers in here, if I have this, and let's put some numbers here, if the limit of h of x as x approaches, let's just say 3, equals 2, and the limit of g of x as x approaches 3 equals 2. And if you know this to be true, if there's f between those two, then the limit as x approaches 3 of f of x has to equal 2. That is the squeeze theorem. All right. There are some limits that we just don't have analytical methods aside from graphing or things like that. And oftentimes things are non-calculator. There are some limits you just have to memorize. There's 3 of them right here. Okay, you just have to know these. These are ones that will show up that it's just expected that you guys know. I hate having to memorize a bunch of things, but in this course, you are going to have to just remember a lot of stuff. And I'll try to teach you some ways that you don't necessarily have to memorize everything, but there are some things you just have to memorize, and these are a couple of them. On the AP exam, you get no formula sheet. You get nothing. You have to remember every single thing, okay? So here we go. The first rule says, if you have the limit of sine of x over x as x approaches 0, so if you see this limit occur, that limit equals 1. And also works if you flip this fraction right here. Now the proof of these, you can look in your book if you would like, but the proofs of these stem from the squeeze theorem to prove that these actually are true. They stem from the squeeze theorem. And then the last one says the limit of 1 minus cosine of x over x as x approaches 0 is 0. Now this part matters because if I said the limit as x approaches 2 of sine of x over x, well then we can use direct substitution and plug 2 in and get our answer. These are ones we have to memorize because if we plug 0 in, we get 0 over 0 and it's undefined and we can't factor or rationalize. So these are just ones we have to know. And in fact, these are true if these quantities here are equal to each other. If these two things are equal, then this is going to turn out to be 1. Here's what I mean by that. If I also have the limit as x approaches 0 of sine of 3x over 3x, so if these two quantities are equal, then it's going to equal 1. All right. That comes helpful in our last example right here. So our last example. Find the limit of sine of 3x over x as x approaches 0. So I tried direct substitution. And I'm going to get sine of 0 over 0, so indeterminate form. But now I can apply this over here. Our issue is, if this is a 3x right here, I need this to be 3x. Well, the great thing about math is you can manipulate things to your advantage as long as you know what's allowed. And that's what algebra is all about. What are you allowed to do? And we're allowed to just put a 3 right here. You're allowed to do that, so long as what you do to the denominator, you also do to the numerator. That's allowed. You're allowed to multiply the top and bottom of a fraction by the same number. So we've met the goal. But now we have this issue. We have this 3 in front of the sign, and that doesn't happen over here. Well, now we use that property that says if you have a constant multiple, where are you? If you have a number being multiplied by a function in a limit, you can actually pull that number out in front of the limit. And that's what happens here. This 3 is a multiple. It's being multiplied by this function here, so we can pull the 3 out in front and write this as 3 times the limit as x approaches 0 of sine of 3x over 3x. And we just talked about that right over here. This is equal to 1. So we have 3 times 1. So 3. So we just work on our manipulation. All right, so you get some practice here, finding limits analytically, but don't lose sight of the concept. You're really finding what the function is approaching as x approaches that target x value.